in the second part of today's lecture, I am going to discuss about lab 1 of this course. As you know that at the start of course we agreed that there will be labs towards the end of this course which will guide you how to implement a DSP filter on an FPGA. So there will be multiple labs in this regard, since we are not having access to the actual hardware at this time. But what we will do now, we will do some simulations first that will guide us to generate a design in MATLAB and convert it into a format that is known as HDL code or hardware description language code, which is required to implement a design on FPGA. So today in lab 1 and lab 2 we are going to learn how to convert a FIR filter design into a related hardware description language code. The hardware description language are of two types. One is known as Verilog HDL and the second one is VHDL, and we will particularly convert our design into Verilog HDL. Verilog HDL has a syntax which is easy to understand, though at this stage it is not required that you know all the details of Verilog HDL. We will simply rely on the generated script by MATLAB, and later on in the next few labs we will learn how to simulate that design before implementation and how to implement the design on FPGA. Once the university is open again, then we will conduct labs where you will physically interact with an FPGA and can test your design in real time. However, I will give you a live demo of implementation on an FPGA during the course of these labs. So there will be total of 5 labs. Today I will discuss about the first 2 labs. I will provide you this lab manual, and beside that I will also provide you any other related material so that you can experiment yourself at home. For lab 1 and 2 you simply need MATLAB. So using MATLAB we will generate a FIR filter in lab 1, and in lab 2 we will generate an IIR filter. At the end of each these 2 labs there is an assignment mentioned, and you have to attempt it yourself, and this will be quite easy to attempt because it only involves the steps that are already explained in the manual starting from page number 1. So in this lab, in the first lab, we are going to design an FIR filter, and I will generate Verilog HDL code for this filter. I am going to use Filter Designer in MATLAB for this purpose to design my filter. It's a graphical interface that permits you to design your filter without writing any code. Definitely there is an option, once you have designed your filter you can convert it into a MATLAB script as well, or even you can store the filter coefficients on your hard drive as well in the form of a MAT file. So we will select the response type, the design method, whether the filter is IIR or FIR, and we'll select the frequency and magnitude specifications, and then we will design the filter. First I will design the filter without quantization. Later on I will apply quantization to the filter and design a quantized filter, and then we will make a comparison of both the designs. So for this purpose, we will make use of an app in MATLAB which is Filter Designer. We simply write the string Filter Designer, both the words are written together, and this will start the app that will guide us to filter design. The earlier process that I explained in my few other lectures, where we made use of MATLAB code to design the filter, that is also the process, and it gives you more control over the design. However, here we can do some simple designs, and additional advantage will be that we can also generate directly the Verilog HDL code as well from this app. So the app has multiple sections. Here the design filters, magnitude, response will be displayed. Here we need to give the frequency specification and magnitude specification, and then we select type of the filter. So let's say we select a low pass. There are other types as well, but we select a low pass filter and we design it as an FIR filter with equiripple design. There are many other options, but those are not of our interest at the moment. You can also do window design, for example. We will be doing equiripple design. Instead of specifying the order, we leave it to MATLAB. So we select minimum order function. The density factor option is selected as 20 in this case. The frequency specification. Now we can select the units as hertz, or we can also use normalize. In normalize, you will be giving the discrete omega values between 0 to 1. So let's select it at hertz. We select a sampling frequency of 48 kilohertz. The passband frequency is 9.6 kilohertz and stop band frequency is 12 kilohertz. So we are designing a low pass filter. The magnitude response specification can be selected either in dB or linear. We select dB. So A pass mean alpha P, which is 1 dB, and A stop mean alpha S, which is 80 dB. So let's make it to 60 dB, for example. After selecting all these options, you simply click design filter and the filter design process will start, and finally the app will show you the corresponding magnitude response of your filter as shown here. So it has designed this filter with order 39. It's a direct form FIR as equiripple filter, and the specifications are same as shown here. You can see that the stop band ripples are at 60 dB and the pass band ripples will be within 1 dB. Now this is the original filter. Now we need to quantize this filter, and for this we can select the set quantization parameter option from this left pane. Before that, let me further describe that if you want to store this filter on your system, so it's very easy. You can select from files menu, you can select the option export. So it will save this as coefficients, and it will save it to either workspace, or you may select as mat file. That's the option which will help you to later on recover this file as well. So we give it the name because it's an FIR filter, so it only features a numerator polynomial. So let's keep it, give it the name num, the vector storing the coefficients, and we export it. It will ask you where to store this file, so we will give it the option and it can save it there. So for example, I say that FIR equi-ripple dot mat, and it will save this file for future use. So the file has been saved on my desktop here, and I can simply call this file inside MATLAB now by we can access it, so changing the location to the folder where the file has been saved, and you can easily right click this file and select the option as for example, if I say open, sorry, I selected the wrong file, the mat file here, so here it is. Now select it and do this import data, and you see that it is showing you this polynomial num which was stored, and the corresponding coefficients are stored here. Total number of coefficients are 40, the order was 39. And later on at any stage you can recall this file in your code by using the function load. So you can also do it as load, call the simply write the file name equi-ripple and then after space you give the name of the variable as well. So it will load this num variable in the workspace, and if I look at here, so this variable has been saved to workspace. You can use this in your code later on. So now we do the filter quantization. So we go to this set quantization parameters dialog, and here in the first display we select, we are going to make use of fixed point representation, fixed point. It will open the related options here. So we have coefficients, input output, and filter internal tabs here. So it has selected a word length of 16. That means there will be one integer bit and 15 fractional bits. So this format is known as Q1.15 format. So we say that we have a number in Q1.15 where the most significant bit is the sign bit, and then rest of the bit, this is assumed. Actually physically this decimal point is not present, but the bits after that are denoted as A minus 1, A minus 2, and so on up to A minus 15. So the weights are 2 raised to power minus 1, 2 raised to power minus 2, and 2 raised to power minus 15. So we select a numerator word length of 16 bit here, as I mentioned 1.15. Then we move to the next part, and here we are going to select the input fraction length as 15, and then we select filter precision, and we select output word length as 16. And fraction length should be remains as it is. Then we move to the filter internals tab, and here we select the rounding mode as floor and overflow mode as saturate. So it will, once the overflow occurs, it will saturate the number to maximum possible number with those number of bits. So for example, in the case of 4 bits, the maximum positive number is 7 and minimum positive number is minus 7. And accumulated word length is selected as 40 here. So after doing all these settings, we do apply, and now it has designed two filters now, where the comparison will be evident inside this plot. If we can maximize it at some point to see the comparison. So the two designs match each other quite nicely here, and because of this we have a filter now that has been designed both using unquantized and quantized coefficients, and particularly for this quantized filter, now we select targets and will generate the HDL code. So we select the command generate HDL, and it will generate two files for us. The extension for Verilog HDL file is .v, and it will generate a source file where the whole design of this filter will be described, and it will also generate a test bench file that will be used during simulation to test this design. So the test bench file, also known as a stimulus, it is used to generate some input signals, vectors, and are applied to the original design, and based on that we can simulate the design and see the related output. So here we select the language as Verilog, the name of the filter, let's say I select it as basic FIR, and the folder where it is going to save it. So you can select, for example, I have selected it as desktop, so it will save it on the desktop. So we move to few other settings now for this filter. Before generating the Verilog code, we go to the global settings, and here as you can see, Verilog file extension has been selected as .v in this case. So here we can comment. This will be the comment that will be represented in the Verilog file. That's just for header that will be added to this file, so it will be a comment only. So going to the ports section, in this part now, in the port section now, we have input port and output port. The input port, let's denote it as data in. This is the input signal for this case, and I denote it as data out or output. Here we leave the settings as it is, and now we move to the next part. Here it will also add, because all digital filters feature two essential signals as input. One is known as clock and the other one is reset. So these are automatically added to the signal, because the filter is going to perform a generate samples based on the pause edge of the clock or the high level of the clock. Usually we have an edge triggered clock, so at the pause edge of the clock, positive edge of the clock, the filter will start its working, and reset signal can reset the design at any time and initialize it. We go to the test bench. Here the test bench file name will be specified. Let's make it as basic FIR test bench, and rest of the settings are left as it is. We don't need to change anything here as well, and that's it. We click now generate. And it will generate for us the corresponding .v file and the corresponding test bench, which will be also with extension .v. So the progress can be seen here on the MATLAB command prompt. So the both files have been generated now. The whole progress was displayed here. There were few warnings, just ignore them, and it has successfully generated the required files now, and it will be stored on the desktop where I mentioned the path. So we can close it now. So our complete filter design is there in the form of Verilog files, where it has generated these. I forgot to add a folder, so we can have a folder as well where we can easily put all the related files in there. Basic FIR, and I copy all these files, related files, to this folder. So you can see now it has generated a .v file and another .v file with name basic FIR TB, which is the test bench for this. So we will use in the next lecture, we will make use of the simulator Modelsim for this purpose. I will guide you how to install Modelsim on your PC. The student edition is free. You can download it from the makers of or developers of this software, which is Mentor Graphics. So Modelsim will be used for simulation purpose. So the design that has been generated inside this .v file and the corresponding test bench, we will learn how to simulate this design. Then the design is converted into a FPGA compatible file using Xilinx ISE design suite. That will be part of our discussion in lab number 4. So the next lab would be next lecture's lab would be based on this simulation. In a similar manner as I did it for the FIR filter, you can also do it for IIR filter and generate the code as well. All the steps are quite similar, except that in the start of the design you have to select IIR filter, and accordingly all the parameters needs to be set, and then after designing the filter you can do all these steps which I did for the coefficient quantization. The details are listed in this manual. I will share the manual with you, and you can easily download the Modelsim simulator on your PC. At this time, if I show you the related files here which have been generated as the basic design file, and MATLAB can open it. It can even be opened in a text editor. So here the basic details are given, but for us here the file starts from this stage. In Verilog, the basic entity that is written where the whole design is described is known as a module. So we have a module named basic FIR, and then in the net list, the list specified after this module is shown here. Verilog allows you to separate the arguments to this entity using comma, and you can even put different arguments on different lines. So clock enable, reset, data in, these are our inputs, and data out will be the output of the filter. So input is clock, this input keyword specifies the input is the clock enable, input is the reset. All these are external signals that will be connected to our filter. And then we have an input signed, which is 16-bit fixed point representation, presented as data in. The length is specified as 15 down 0. This column means down, so it's a 16-bit number, and output will be a 16-bit output as well. And rest of the design has been described here. You don't need to go into the details of this design at this time. This merely describes your filter. Once the module is completed, so you need to put this word end module to mark the end of this entity module. So this is the complete design of your filter. The direct form FIR filter, which is equiripple, and it is a low pass filter having input which is quantized to 16-bit in the Q1.15 format. The test bench, on the other hand, is stored in a separate file. So here the module name is test bench. Here you don't need to specify the inputs directly, and this test bench will generate the signals clock, reset, clock enable, data in, and will pass it to the module, and based on this we can simulate that design and can record the output of this filter to verify whether the filter is producing correct sample values or not. So we will learn this in the next lecture using Modelsim. Till then I will send you a link on Microsoft Teams, where you can follow that link and can easily download the Modelsim simulator on your desktop and can install it, and we will learn how to use it. So here I can show you the interface of the Modelsim. So its student edition is free and you can install it, and its license is valid for 6 months initially, and you can renew the license later on. So Mentor Graphics is the developer of this software. So here we will learn next time that how we can use this environment and can easily test our design. So now you can also try this design, IIR design as well, and at the end of each of these manuals you need to solve an assignment inside this Filter Designer app. In the case of IIR, you need to design a band stop filter, which will be elliptic band stop filter, and in the case of FIR, the lab assignment is mentioned on the last page, where you need to design equiripple band pass filter using this app. All the specifications are listed in this table in both cases.